Hi, everyone. Okay, so this is going to be our last topic within divide and conquer algorithms. We're going to go over the fast Fourier transform, and then we'll see how it actually provides us with an even faster algorithm for multiplying two n-bit numbers. So as a motivation, consider the problem of multiplying two polynomials. So you have, let's say, a of x is this degree d polynomial with coefficients a0 through ad. B of x is a d degree polynomial with coefficients b0 through bd. And we want to obtain the polynomial that you get by taking the product of a and b, which is going to be a polynomial with some other coefficients and with the highest degree of 2d. Now, when you multiply this out, right? This is just, think about just putting brackets around this, multiplying the b, and you get, you collect all the like terms with the same power. And what you're going to get is that the kth coefficient in the product is just going to be all the terms that have x to the power of k beside them. So there's going to be an a0 bk, a1 bk minus 1, all the way up to ak b0. And it looks like a sum from 0 to k of ai b k minus I. And here, the only thing, just so I can write this sum going all the way from 0 up to k, we say that if I is greater than d, then ai and bi are 0, right? Just so that, because this sum will try and access an element of a or b that's larger than the highest coefficient. So we just say those coefficients are 0, basically. So if you look at this, right, you have to compute from C0 up to C2D. So you need to compute 2D plus 1 coefficients to find the polynomial C. And each requires order D time to compute because you have to compute this sum. So order D time to compute using the above expression. So we're getting 2d multiplying big O of d, and this algorithm runs in d squared time. This simple, just sort of by definition method for computing the product. Right, so just to clarify, these in this polynomial, x is a scalar, right? So a, when I plug in a value of x, a of x just gives me out a number. And same with b. And so this c is also just a number, right? When I plug in any given value of x. So why would I want to multiply two polynomials? Sorry, just one second here. So first thing is that the output of a linear system is the multiplication of two polynomials. You may have seen this in ECE406, for example, where we take the input and the impulse response, and we take a convolution of then the impulse response, right, is a convolution of the input in the system, basically. And then the other one, which maybe is more important for us, is it will actually provide a fast algorithm for scalar multiplication. So this is for n-bit numbers. And it will beat our first two algorithms, our divide and conquer one and our that other one that we wrote back in the algorithms with numbers section. So can we do better than the naive method, which gave us d squared time? And that would actually, if we used it for multiplication of n-bit numbers, when I tell you how that works, it would give us an n squared time algorithm, which wouldn't be better than what we found. And the key observation is that if I have a polynomial, a d degree polynomial, we can characterize it two ways. The first is in terms of its coefficients, a0 through ad, and the other is in terms of values, which we call its value representation. And that just has to be its value at d plus 1 distinct points. So to give you just a simple example of this, let's say I have the polynomial a of x equals 2x plus 5. So the degree of this polynomial is 1, right? The highest power of x is 1. The coefficients, all right. The coefficients are a0 equals 2, a1 equals 5. And that, of course, defines the polynomial. And the other would be the value representation. Value representation is just evaluate that polynomial at 2 points. So let's take any two values. Let's say x equals -1 and x equals 3. And then we get a at -1 is -2 plus 3 plus 5, that's 3. And we have a evaluated at 3 is 6 plus 5, that's 11. And this, so this is one representation of the polynomial. This is also a representation of the polynomial. There's only one polynomial of degree 1 that passes through these points, right? And basically, if you think about it, and this is just 2 points on a line specifies that line, right? If I give you 2 points in the plane, there's only one line that passes through those. If I instead have a parabola, right, something of degree 2, then any 3 points in the plane uniquely describes the parabola. 4 points describes a cubic, 5 points describes a quartic, and so on, right? So the idea for polynomial multiplication is going to be the following. We want to multiply 2 degree D polynomials and get their product, which is just another polynomial. We pick a number n that's at least as big as 2D plus 1, because there's going to be 2D plus 1 coefficients in C. And so we pick 2D plus 1 unique values. We compute the value representations of A and B, right, by just evaluating A and B at those numbers. Then we compute the value representation of C. So we get the value representations of A and B, where we have these unique numbers. From that, we compute the value representation of C by just saying C at the point xk is just equal to A at xk multiplied B at xk, right? This is a number, and then B at xk is a number. And so this just gives us the value representation of C. And then we need a way to convert from the value representation of C back into the coefficients for C. So then we need something to recover the coefficients from its value representation. So let me give you an example again, just to sort of illustrate this idea of converting between value representation and coefficients. So let's take another polynomial. AX is 4x squared plus 2x plus 1. So it's degree 2. Its coefficients are A0 equals 1, A1 equals 2, A2 equals 4. And let's come up with a value representation. I'm going to pick some arbitrary points. X0 is 0, X1 is 1, X2 is -1. Then the value representation, A at X0, is just going to be plug in 1 here. I get 4 plus 2 plus 1, so it's 7. A at X1 is going to be, sorry. X0 was 0. Plug in 0 here, I get 0 plus 0 plus 1. That gives me 1. x1 is equal to 1. So I plug in 1. I get 4 plus 2 plus 1. That one is 7. And then a at x2 is minus 1 squared. That's going to give me 1. So that's 4. Minus 2. That's 2 plus 1. So that's 3. And if I give you these 3 values, that then uniquely describes a parabola, right? From that, there's only one equation of this form with free coefficients that passes through these 3 points at these 3 values, right? Has these 3 y values essentially at these 3 x values. So if I give you the value representation, if I just gave you that at these 3 values, this is at these 3 x points, these are the values, then how do I recover the coefficients? So to find the coefficients, from the value representation, I want to find an a of x of the form a0 plus a1x plus a2x squared, right? And so I know that a of 0, the things I'm given are a at 0, a at minus 1, and a at plus 1, a at minus 1. Going to arrange them into a vector. So those values, which we just wrote above, were 1, 7, and 3. And that equals some matrix multiplying the coefficients a0, a1, a2. So when I plug in 0 here, I'm going to get a0 plus a1 times 0. So this is a 0. a2 times 0 squared. So that's a 0. When I plug in 1, I'm going to get a1 or a0 plus 1 times a1. So this is 1. And then the x squared term is also going to be a 1. When I plug in minus 1, the coefficient that multiplies a0 is again a 1. The coefficient that multiplies a1 is a minus 1. And the coefficient that multiplies a2 is a 1. Call this thing m. Right? So then what I have is, if I know this and I want to solve for a0, a1, a2, then basically what I have to do is invert this matrix M. So I get that a0, a1, a2 is equal to M inverse multiplying the value representation, 1, 7, 3. And so basically, going between the coefficient representation and the value representation is like solving a linear system of equations. Going from the value representation back to the coefficient representation is just this, taking the inverse of this matrix and multiplying it by a vector. And the big thing is that when if we carefully choose, like here, I kind of just chose arbitrary values for x0, x1, and x2. If we kind of carefully choose them, then this computation will end up being easier, right? Which is this final thing, recover the coefficients of c of x from its value representation. So basically taking this inverse will end up being easier to do. So I need to fill in several details to actually tell you how this algorithm works. The first question is, which numbers should I choose, x0 through xn minus 1? And then there's, how do we do evaluation and how do we do interpolation? So evaluation is this step where I compute the value representations of A and B, and interpolation is the step where I find the coefficients for the polynomial C from its value representation. And it turns out the fast Fourier transform tells us how to do all of this, basically. And the selection is kind of weird. So it might throw you off a little bit when you first see it. To begin, we define the complex number, omega, which is e to the power of 2 pi I over n. So here I is the imaginary number, square root of -1. And then we consider for selection, rather than using real numbers, we're going to use complex numbers. It turns out that that gets us a big time savings to use complex numbers. And so we use this selection for x0 through xn minus 1. We go xj is omega to the power of j. So what are these points? You can really think of them as complex numbers. I mean, in polar form, right? So this gives us an angle, and then the length is the coefficient that's out in front of this exponential. And so they're a distance 1 from the origin at some angle. And so let me just show you what these points look like. Take n equal to 4. Then omega is equal to e to the power of, if we look at it, it's 2 pi I over 4. So it's going to be pi I over 2. And then if I plot these points in the complex plane, this is the real axis, the imaginary axis. I need to draw a circle here like that. Not perfect, but suppose that's a circle of radius 1, then the points are x0 equals omega to the 0, x1 equals omega to the 1, and so on. And so omega to the power of 0 is just going to be e to the pi I over 2 to the power of 0. That's this point right here, right? It's e to the power of 0. The next point is going to have an angle of pi over 2. So this just looks like e to the 0 times I pi over 2. So it has an angle of 0. This one is e to the I times pi over 2. It has an angle of pi over 2. So this is omega to the 0. This is omega 1. This point here is omega squared. And this point down here is omega cubed. So these are the points that we're going to use to evaluate the polynomial. It seems kind of unusual because I'm plugging in complex numbers, but you can do it, right? I mean, if I take this polynomial, I can plug in a complex number here. It evaluates to something. It's going to be some complex number, but that's fine. And the reason for it, I'll tell you in just a second, like why we're doing this particular selection. But these points, x0 through xn minus 1, are called the nth roots of unity. They are the complex solutions to the equation z to the power of n equals 1. Right? This to the power of n equals 1. That's true. This point to the power of n equals 1. This point to the power of n equals 1 as well. And this one to the power of n equals 1. Those are the 4 solutions. Sorry, to the power of 4, I mean to say. So these are the 4 solutions to the equation z to the power of 4 equals 1. Now, how does this help us? Why am I doing this? And the reason's pretty clever. So how does this selection help us in evaluation? To understand, we're thinking in the context of divide and conquer, which is always that we take something and we split it into 2 pieces. So right now, let's think about evaluation. We're trying to evaluate a polynomial a of x. And to do it, we're going to split it into 2 polynomials. It's even and it's odd powers. So for example, if I have a of x is some polynomial, let's say it's 1 plus 2x plus 4x squared plus x cubed plus 2x to the 4 plus x to the 5. I split it into its even and its odd powers. So its odd powers are, its even powers are 1 multiplies x to the power of 0, that's even, plus 4x squared plus 2x to the power of 4, that's its even powers. And then its odd powers are 2x plus x cubed plus x to the power of 5. And then I noticed that the second one, there's an extra x in all of them. So I can factor out 1x. And I can write this as 1 plus 4x squared plus 2x to the power of 4 plus factor out the x. And I write it as 2 plus x squared plus x to the power of 4. And this is some polynomial. And this is also some polynomial. And the thing that you notice is in each of these, you only get powers of 2, right? Even powers. And so I can think of this as a polynomial in x squared. And I can think of this as some other polynomial, a odd in x squared. Right? So a odd of y is 2 plus y squared. If I plug in x squared into this, I get 2 plus x squared plus x to the power of 4, right? A even of some argument y is going to be 1 plus 4y plus 2y squared. And so the thing that you see, right, is I've managed to break this one polynomial of degree 5 into 2 polynomials of lower degree, where I'm doing this kind of unusual thing in that I'm plugging in x squared into them. So a even and a odd are polynomials of degree less than or equal to n over 2 minus 1. And so this is the trick. I write ax as a even evaluated at x squared plus x times a odd evaluated at x squared. And these polynomials are of lesser degree. And so now the whole reason that I pick these particular numbers to evaluate at is that it's going to end up being useful. When I try to evaluate ax at one of these numbers, I instead have to evaluate a even at x squared and a odd at x squared. And so that will end up being easier with those unusual kind of complex numbers. So this suggests a divide and conquer approach for evaluation. To evaluate ax at the nth roots of unity, which is omega to the 0 up to omega to the n minus 1, we need to evaluate 2 polynomials, a even of x squared and a odd of x squared at these points. However, if n is a power of 2, then letting omega n equal this, we see that what happens when we square these omegas. So we have, let's say, omega n j. Let's say we take the jth one and we square it. That's going to be omega n to the 2j. Plug in the definition of omega n. It's going to be e to the power of 2j multiplying 2 pi I over n, which equals e to the j 2 pi I over, and then let me group. What I'm doing is I'm stealing one of these 2's and I'm bringing it into the denominator of the denominator. And so, right, like this 2 is, let's say that 2 right there. And so you can see that this then is e to the j, sorry. If we look at this now, it's j multiplying 2 pi I over n over 2. So these are now the n over 2th roots of unity. And so when I take one of these nth roots of unity and I square it, I wind up with the n over 2th roots of unity. This might be a little bit confusing, but squaring the nth roots of unity gives us 2 copies of the n over 2th roots of unity. Maybe I can show you via an example that will make this a little bit clearer. So let's take the 8th roots of unity as an example. So let's take n equal, sorry, let me go back to that. Let's take n equals 8. So our omega is ei to the 2 pi over 8, which is ei to the pi over 4. So we get that omega to the power of 0 is equal to 1. Omega to the power of 1 is ei to the pi over 4. Omega squared is ei to the 2 pi over 4, and so on. And so these points are just spaced out on the unit circle by an angle of pi over 4. So they're going to be the points here, here, right, where this angle is pi over 4, this angle as well. So this is omega to the 0, omega to the 1. And these are the 8th roots of unity. And now let's say I square them. So square each one of those numbers. Then what I get, real, imaginary, real again. So when I take 1 and I square it, I just get 1. Oh, I guess I have to draw my circle again. When I take 1 and square it, I just get 1. So this is omega to the power of 0. When I take omega 1 squared, rather than it being at an angle of pi over 4, it will be 2 times pi over 4, which is pi over 2. So omega 1 is here. Right, basically, in squaring, I just double the angle. So this omega 2 was at an angle of pi over 2. Now it's going to be at an angle of 2 pi over 2. So it's going to be here. Omega squared. And then omega cubed was at an angle of 3 pi over 2. So now it's going to be, 3 pi over 4. And now it's going to be an angle 3 pi over 2. So this is omega cubed. Omega 4 was at an angle of pi over, or at an angle of pi. So now it's going to be at an angle of 2 pi. So this will also be where omega to the power 4 is. This will also be where omega to the power 5 is. This will also be omega 6. And then this is also omega to the 7. And so this is 2 copies of the 4th roots of unity. And so what we see is we have the 8th roots of unity, we square each one of them, and then they sort of snap onto just the 4th roots of unity. If I were to square these, I would just get the 2 roots of unity, which would just be this point and this point. If I square it again, I would get all 8 points located right here. And so with this, we get the following divide and conquer structure for evaluation, which is to evaluate a of x at the nth roots of unity, omega's n to the 0 up to omega n to the n minus 1. We instead evaluate 2 polynomials of half the size, a even and a odd, at the n over 2th roots of unity. So to evaluate a of x at the nth roots of unity, we evaluate 2 polynomials of half the size at the n over 2th roots of unity. And this then is a divide and conquer, right? Instead of solving one problem of size n, I'm going to solve 2 problems of size n over 2, and then I have to do some work to combine and whatever. And so this is only to compute the value representation of a of x. So right now we're still just talking about this step right here. Rather than computing all of these points, I'm going to do this clever thing where instead of evaluating this at n minus 1 points, I'm going to find a even, find a odd, and evaluate each of those at n over 2 points. And then it's going to be recursive, right? Instead of evaluating a even and a odd at n over 2 points, I will divide those into 2 pieces and evaluate them at the n over 4th roots of unity. That's going to get me the value representation. From that, I can compute the value representation of C, and then we're going to have to figure out interpolation, and there'll be a really clever solution for that. So I'm going to break this fast Fourier transform lecture into 2 parts. This is the end of part 1, and join back on part 2, and we'll continue right from here. So thanks, everyone.